Hello, everybody. So my talk today is about MICCAI to market. And one main motivation from me personally, probably, talking about this topic is the city that I'm working in for several years already. That's Heidelberg at the DKFZ, German Cancer Center. And the German Cancer Research Center is sitting on a campus where we are really tightly interacting also with the university clinic. So from the beginning on, I had the clinics next door, and I had the endeavor basically to translate our methods into the daily clinical work. So how does our typical scenario nowadays look like? So we have some kind of a method, may be a classifier, and we usually nowadays train it using annotated training data. So in a perfect world, we would have unlimited amounts of annotated data, but in reality, annotated data sets are really hard to access. And it's also very hard to motivate the experts for data annotation. So it comes down that this is really quite a problem if you think about building methods that actually work in the real world. One example, of course, you've already mentioned NNUNet. So that's just the ability now to apply such methods to many, many different problems and perform nicely without any expert interaction further needed. So this, for me, increases basically the pressure to build pipelines that allow translation of such methods into the clinic. So if you actually look at the data that we have available in normal scenarios, that's only the small peak of an iceberg, and the rest is basically not available to us. Even though some of it may be shareable, other data sets might not be shareable at all. So I think one important motivation on the way to the clinic is to actually make more data sets available for research. May it be by enable sharing such data sets, or may it be by synthesizing data sets, or may it be by federating our infrastructure so that we don't have to send around the data, but we can send around the methods. And we've been thinking about this for quite some time now. And if you do think about this, you need to think about the stakeholders that you want to address with your work. And these are, in principle, the clinicians, but of course also the data scientists. And so if you really want to build something for clinicians, you have to make sure in the end that you impact their clinical lives. That means we need to build some support either for clinical studies or for the daily routine work. And that also includes facilities like DICOM viewing, but also data exploration, cohort building, and these kind of things. And at the same time, we have to adhere to the principle that data sharing is difficult. So I mean, it's possible in some cases, but still difficult to achieve. So we have to minimize somehow the amount of data sharing being necessary. And last not least, in order to fulfill the requirements of the clinicians, we have to build things that are easy to use. So there cannot be any coding necessary in order for data annotation or algorithm training or application of algorithms. On the other hand, we have a couple of requirements coming from the data scientists. Of course, we somehow need to enable interaction with the clinical IT landscape. For example, PACS connectivity is something we need to think about. We need to think about things like cohort selection, but also object storage for non-DICOM data, user authentication, and stuff like this. And in the end, we also need GPUs available in the clinic and scalability of our computing capabilities. And in terms of applications, we need powerful pipelining systems. We also need utility structures like for data conversion or anonymization of data sets. And all this needs to be as simple as possible and needs to be highly standardized. So to give you a little bit of history of where we come from, we have been asked to build the joint imaging platform That was nearly 3 years ago, 2018. The joint imaging platform was or is a strategic initiative of the German Cancer Consortium, DKFZ. And the aim here was to build a technical infrastructure for modern and distributed imaging research in Germany. So we interconnect the 10 most important clinics here in cancer research with the political aim to strengthen interaction in this network, strengthen multi-center collaboration, but also to build a distributed network for research and standardized image computing. The technical aims of the joint imaging platform were not only federated learning, but also the ease of evaluation of methods in the network. So if somebody comes up with a new evaluation tool or with a new assessment tool, then to make it easy to distribute this tool, and also to address all the regulatory and ethical and legal constraints going along with that. So this joint imaging platform was an important point in my research career in order to tackle actually the gap between MICCAI and market. Looking at the platform a little bit more into detail, so it aims at an on-premise deployment. So the platform is going to be deployed in each clinic. It's embedded inside the clinic and aims then to standardize basically the access to the clinical IT landscape, which can be highly heterogeneous. Second, joint imaging platform is made for processing, so it allows pipelining that easily scales also to large-scale image processing. And last not least, it eases the distribution of algorithms and thus also paves the way for future federated learning applications. So as I said, we started in 2018 with this platform and have seen several releases. In October 2020, we had the release of an open source toolkit called Kaapana, and this is actually the basic building block that we use to build the JIP. So Kaapana is a toolkit that allows you to build platforms like the JIP. And it's open source and also available to you. Some of the challenges that we have met in this joint imaging platform consortium are published in this publication here in JCO Clinical Cancer Informatics. So here we're talking a little bit more about the diverse local policies that you will enter if you looking at distributed systems. So each clinic in the end has its own policy, and we are looking into problems that even if we don't have any outside connection from the clinic outwards, there are still quite heavy security and privacy measures that have to be met in Germany. And we're also looking at things like usability and metadata. Metadata is of course an important problem because it can be highly inhomogeneous across sites. Okay, so the Kaapana toolkit, as I said, it's the technical backbone of the JIP, which was our first major project in this direction. It allows you access to many standardized interfaces and data formats, each of them open. It has been built upon private cloud technology. So here we're taking advantage of large-scale infrastructure that is available and called private cloud technology, and it's already established in many fields, also in industry, and it's openly available. It's in principle a web-based infrastructure that allows you to build platforms that are decentralized or centralized or mixed, as you like. And I see Kaapana also as a provisioning platform. So you can use Kaapana as an operating system, basically, to provision your methods. It can be analysis methods, but it can also be complete desktop applications, Windows applications, any application, or things like OpenClinica or XNAT can also be provisioned by Kaapana. So Originally, the development team was only 2 persons, Jonas Scherer and Klaus. I think they also joined us today here. Over the years, more and more people have joined, which you can see on this slide. And I think this team has done a great job in selecting the different components and making all the small decisions that are necessary to make in order to build such a platform. So from a technical point of view, the platform consists of a bunch of microservices or components, as you wish. And all these microservices are hosted in a Kubernetes cluster. So on this slide, I show you a little overview of some of those components. They are structured in different namespaces. For example, the namespace base is responsible for the user interface and also platform management. You can see it on the top left. On the top right, you can see store, which handles image and non-image data storage. Monitoring is basically for system observation. Meta is handling all aspects regarding metadata, so metadata exploration, but also cohort design, which is extremely important. System is for services like user authentication and also network management. And last not least, Flow provides everything that is necessary in order to allow the processing on the platform. And you can see each of these components here live later in the live demo, which is recorded in video, I must admit. Okay, so one important, maybe the most important aim of Kaapana is that it should provide you with the necessary tools. It should be a toolbox for you to create customized platforms for different scenarios. And to achieve this, Kaapana builds heavily on the concept of microservices or components. And many things that you might need are already there. And luckily, if there's something not here yet, then it's very easy to integrate new things. So Kaapana consists of building blocks that you can put together as you like. Second major aim is to facilitate in the end the deployment of clinical workflows. So let's look at such a typical workflow. For example, you might be in a situation where you need to get data from the PACS, and then you need to think about anonymization, pseudonymization. You want to convert these files into DICOM, from DICOM to Nifty or NERD. You want to implement then your own algorithm or application to work with the data. And in the end, you convert the results back into DICOM, and you might want to have some illustration of the results. So if we now look at what Kaapana offers to you already, you can see that most of these aspects are readily in place, which leaves you only with the part of implementing basically your own algorithm and integrating it into the platform. This can be easily done using the App Store, which handles all extensions to the platform. So in the App Store, you can install components like algorithms. It's extremely easy, really, and scales really very nicely. Can be any application. Such an extension can also be a web-based application, such as a Jupyter Notebook for data exploration or whatever. Today, we have many partners already in Europe that we are working together to deploy and use this platform. There are many ongoing projects that use Kaapana. One I've already mentioned. You can see it here on the left side, the joint imaging platform. It's up and running in 11 university clinics. And it's also seeing first projects that are starting to use the platform for multi-center clinical studies and so forth. Second example would be the Raccoon Radiological Cooperative Network in Germany. And this is really something that came up during the pandemic. There was the necessity to interlink basically all university clinics in Germany. So it's 36 university clinics in order to come up with large-scale annotation and collection of COVID-19 CT imaging data sets, including structured reporting. And Kaapana is being used as an important basis for this Raccoon cooperative network. TFDA is a project that started in 2020, and here we are building on the next generation methodology for security and trustworthiness. And DART is an example of a European project that's also based on Kaapana. And there are many more examples. So let's take Raccoon as an example here. So within Raccoon, I told you it's 36 university clinics, and in the end, in each of these clinics, there's one server running. And this server is communicating directly to the PACS, and the clinicians have access to the platform via a browser. And in the end, you can integrate your own methods using the central method repository in form of Docker images and a central Docker registry. So in Raccoon, we opted for a model which is not completely distributed, but it has central and decentral aspects to it. So in each clinic, there's a node installed, and this node has powerful access to GPU computing, has also all methodology required for the identification of data, and can communicate to the central component in order to communicate then de-identified data. And the central component is basically handling all the cross-site collaboration and analysis, and provides a real-time view of the project progress, and also allows scenarios like training and validation of AI models. So let's take a quick glimpse at the current workflows that are already in place in the platform. So for example, you might be interested in annotating data. So here you could use Kaapana in order to define the cohort that is interesting for you. That would be done in the metadata component. Then you would choose your component for data annotation. Here it is an MICCAI, which is used for data annotation, which is running inside the browser here as a service. And then you would have communication to the internal PACS in order to communicate your annotated data sets, DICOM-sec, for example. So once the data annotation is complete, you might be interested in training in NNUnet. So here, again, you would select your DICOM series. You would then initiate the training procedure just by clicking on it, basically, and then the model would also be communicated to the internal PACS as a DICOM object. Once you have maybe segmented your structures using NNUnet, you might be interested in a typical radiomics workflow. So again, here you would select your segmentations and images, and then you would calculate your features using some kind of routine. And you could then store your results, for example, as XML in the menu object storage for download. And as I said, all this is in principle also possible if we go federated, which is, I would say, in development. So all the local sites would generate their models. They could be pooled, and this would be centrally handled by JIP Central in this scenario here. And the combined models could then be redistributed to the sites. So now I would really like to give you a short impression of the system itself. And for this, I'm going to stop my sharing here and switch screens.
So, hi and welcome to our Kaapana demo. This will show you basically the default configuration of our framework. It will include most of the most common use cases, services and tools we already have included into the framework. But of course, a framework is meant in a way that you can adjust it the way you need it. So in the end, you will probably build your own configuration for a platform for the special project you try to handle with it. In the beginning, you will be presented with this nice login screen, and after the login, you will be on the main user interface, which is the landing page. The landing page is the main user interface to our platforms. So what you see is like one user interface which combines all the other user interfaces from the different services which are running in the platform. It is all browser-based, so all of them are web services, and you can access everything via a normal web browser. So that's what you see here. It's basically just a website. And we have split the platform in different sections, what you can see on the left-hand side in the main menu. So the first main section would be called Store. And as the name implies, Store handles everything which has to do with data storage and data management. Since we are very focused on data standardization, and the most common data format in medical imaging, especially in clinics, would be DICOM, we are also very DICOM focused. So what we try is to store everything we consume and we produce in the DICOM format, which would allow us to have a great compatibility to all the other different clinical systems, and also the platform instances between each other would be highly compatible when they stuck to this DICOM format. And as usual with DICOM, DICOM data is usually stored in a PACS. So what we also did is we included a PACS, a research PACS system, into the platform with DICOM for Share, which is holding and managing all the DICOM data which is currently stored on the platform. How can you get data into this? So you can send DICOM data the normal way, for example from your local research PACS or your local clinical PACS, or just from any computer. With the DICOM send command, you can basically just send DICOM images to the platform, and they will, as soon as they arrive, they will be included in the platform. The second way would be like we have this data upload section here, where you can just drag and drop a zip file with DICOM files, and they will also be uploaded into the platform. The second part of the store section is the OHIF viewer. So OHIF is basically a web-based DICOM viewer where you can have a look at the data which is stored on the platform. So no surprises here. So you have the basic tools, and you can have a look at the data, which is also neat that it's not only the images itself, but you can also view, for example, annotations, which is super important, especially for machine learning. And the last section with Minio is an object storage we included, because even though we are very focused on DICOM, not all the data can be handled in DICOM. So, for example, it doesn't necessarily make sense to store processing results in DICOM. For example, Radiomics features, huge lists of Radiomics features, doesn't always make sense to store them in DICOM. So for all the cases which are not applicable for DICOM, we have this object storage, which basically allows to store and manage any kind of data. So the second main section of the platform is called Meta, and as the name implies, it's all about metadata which come with the DICOM images sent to the platform. So what we do is, when the images arrive at the platform, we extract all the DICOM metadata, like the DICOM headers, from the DICOM itself and feed it inside a search engine. And this allows us to create these nice dashboards, what you can see here, which is basically presenting you all the information which comes additional to the imaging, the raw imaging data itself. So what you see here is what we call our general purpose dashboard, but it's just one view of the data, and like the idea behind it is that you create more dashboards which have a specific view on the data, what you can see later. So what we can see here is like the most important information is there's around 36,000 series stored right now. You can see some patient information like gender information, obviously what kind of modalities are currently stored in the platform. But also like line graph with the distribution of patient age, size, gender, and so on. So this is just, like a neat way for data exploration to get an idea what is really stored in the platform right now. But it is not only for data exploration, it is also what we call cohort selection or data selection. So if you want to use data with an algorithm, these algorithms typically are designed for a specific format, specific modality of data. So if you have an algorithm predicting brain tumors, it wouldn't make sense to give it a CT image of the chest area. So what we need to do is we need to be able to filter all the data we have on the system to narrow it down to only the data we need for the specific algorithm. So let's do that. You can also do it on these dashboards by just clicking on these visualizations, and data will be automatically narrowed down to the filters you created. So if you click on them, what you see is on the top left there will be a filter created, and the whole data will automatically be narrowed down to whatever you selected. So I'm going to start an NN unit prediction, which is designed for abdominal CT images. So what I did, I already selected a CT filter, and the second thing I need to do is I need to limit it down to abdominal data only. So the way I will do it, like here's the body part examined part, and I will just go through it until I find the abdomen. So I will just take that, and then we see, okay, we have found now around 900 series, which has the body part examined abdominal. So that should be fine for the execution of the NN unit. And then we come to the triggering of the algorithm itself. So how we do that is we have this drop-down menu, which lists all the different pipelines, the data processing pipelines we currently have installed on the platform. So what you can find here, for example, is also the NN predict, which is basically the workflow for NN unit prediction or inference with pre-trained models. So let's just select that and click on start. And what you see here, it's a customized dialog, so every workflow can specify the dialog it needs for all the different parameters which are possible with this method. So in this case, here's a list of all the different pre-trained models which are currently available for NN unit. So let's select the task 17, which is basically a segmentation of what you can see here. It's like a whole lot of different abdominal organs. And you also see it expects CT imaging and the body part abdomen. So we already have these two filters here, so that should be fine. And down here you see like limit cohort size. So we found around 900 series. For this demo case, we don't want to execute all of them, so I will just limit it to 5 and then click start. All right, so we get this confirmation that everything was successful, and it will be like the query we created here with the filters will be handed over to the next section, which is called the flow section. And the flow section really is responsible for all the data processing which is happening inside the platform. So from different processing pipelines for machine learning, but also other pipelines like the extraction of DICOM metadata is handled in this part of the platform. And we use Airflow for this, which is a workflow management system which allows you to build these pipelines and also manages the execution, that it happens in an organized fashion. So if we have a look at the list, which shows us all the currently installed processing pipelines in the platform, we can also find the NN unit predict we just triggered. And what you can see here is basically all the components the processing pipeline is built of. So everything starts with the get input data processing step, which uses the query we just created in the meta dashboard to get all the corresponding DICOM images from the integrated research packs. So this will download all the corresponding images and convert them in the next step to the NIfty format, which is accepted by the NN inference itself. So in parallel, it also organizes the selected NN unit pre-trained model to finally execute the inference itself, which is the NN unit inference processing step. This will finally result in a NIfty containing all the segmentations, which we take to convert it back into the DICOM format. As I said, we are very focused on data standardization, and of course, if it's possible, we really try to convert our processing results back to the DICOM format. And in this case, it produces segmentation, so the DICOM format corresponding to that would be DICOM segmentation, which we use here. And finally, the result will be sent back inside our data management system, where it will be available in the research packs, but also in the meta dashboards. It will show up. So what's also very interesting is that each of these processing bubbles you see here is when it executes, it's an independent container running, which means it scales very well, since you can easily, so if your hardware is strong enough, you can easily trigger like 10, 15 or 20 NN unit inference containers in parallel, which of course speeds up the process very much. So you would be able to create annotations, automatic annotations very, very fast. And what you see here is also like a live view on what's going on. So the dark green means this has been already successfully covered, and the light green means this is going on right now. So the NN unit inference container is running right now. And if I refresh it, yes, it's still running. So after time, it will be done, and all these steps will be followed, and then it's basically finished. When they are finished, and I think a couple of them are already done, like this pipeline is already done, they will show up in the segmentations view of the meta area. And this is interesting because it is like a specialized dashboard which is focused on annotation, especially segmentation annotations. So the modalities which are pre-selected are DICOM segmentation and RT struct, which are in the community like the typical DICOM modalities which contain segmentation information. So you see on this instance, which contains a lot of TCIA datasets, there's already a lot of segmentations available, like 4,000 series containing segmentation information. And all these different information which is needed for the data exploration, but also data selection, is again presented in these visualizations. So you can, for example, see what kind of labels are present in the different segmentation objects, or you can also see, is it a multi-segmentation, multi-label segmentation, or is it a single label segmentation, and also what kind of algorithm created this kind of segmentation. So we are on the search for our NN unit created segmentation, and NN unit encodes the tasks it predicts within the series description. So we should be able to find it in here. And there we see it. Like here's the NN unit task 17 with the 5 images we just selected, and we can just filter to that. And then we see like these are the 5 studies we just made our predictions on, and with a single click it will automatically open the OHIF viewer, where we can have a look not only at the base image where the segmentations have been generated on, but also on the segmentations itself, of course. So when we click on segmentations, this usually takes a while, but there you see all the segmentations which have been generated are loaded, and you can just click on them and you see you can see they are also visually presented within OHIF, which is really nice. So there you have it. That's basically just the NN unit inference with the pre-trained model we just did, and it's available now in our OHIF viewer, which shows us the data which is stored in the local research packs inside. The last section I would like to show you is extensions. And extensions can be seen as an app store for Kaapana instances, where you can install additional services and processing pipelines on the fly within your instance. So, for example, the NN unit, what we have seen before, it is listed as an extension within here. So you can easily install all the functionality of NN unit, including also training within your Kaapana instance. It is also possible to install continuously running services, like for example, the research packs would be such a service. And you can easily install additional ones, like in this case, there's Code Server, which is a browser-based environment for developing code. So you could change your processing pipelines directly via the browser on the server itself. So that was only a short look on Kaapana. There are many more things to explore and to try out yourself. We hope we could give you a small impression of how the framework works, how it looks like, and what it's capable of. Maybe you're now interested and have some ideas how to use the system for your own projects. We are always happy to hear about these ideas and to discuss your questions. So always feel free to reach out to us. So thanks for your attention.
All right, thanks a lot, Jonas. So in case this got you interested in Kaapana, then please reach out to us. Your first steps would be to set up such a system on your own, which is quite easy. So we have pre-built images, which you can install from Docker registry. Just check out the getting started and the user guide at the address given here. And play around with the different components, and you will see it's quite nicely, quite easy to understand and getting too used to it. So if you're interested in deploying your own algorithm, there's also development guides that you can follow. So you would create your own very simple graph, DAG, to basically define your own pipeline. And all this is, of course, very nicely explained. You would basically tell your algorithm how to work with the folder structure that is used by our system, Dockerize your algorithm, and then create your operator that basically runs then in the Kaapana platform. And that would be all you need to do to deploy your algorithm within the clinics. If that sounds cool, I would also like to highlight one of the tasks in the upcoming hackathon on October 23rd, 24th. So feel free to register and participate here. This will also be all about deploying your methods within the Kaapana platform. Will be about containerization, and also we'll look at the anonymization of document images. So thanks, Klaus, for hosting this and organizing this hackathon idea. If you want to know more, please get in touch. There are several ways of doing so. And for me now, the only remaining thing is to say thank you for listening, and also thank you to my team that has done all these nice developments. And of course, also thanks to our collaborators and funding agencies. And looking forward to your questions now.